Hello, participants, and once again, welcome to the e learning course Chromatography, jointly organized by Sheth M and Science College, Patan, Gujarat, and DIPAM Foundation. Friends, today we are going to learn on day 2 a very important concept in chromatography, rather to say, a very basic concept. But before I start with the concept, day 1 was really well from your side. You were really enthusiastic. Few of the feedbacks that I would like to discuss with you before I move on included four major things. One, that sir, please make the animated video on the complete screen rather than on a circular effect. I have tried to implement that in this current video. Second thing was, try to raise the voice of the animated video. I have even tried my level best in doing that. Third important thing was, sir, can we increase this little speed of your speech? You are going little slow. That makes the lecture of an hour and it is little longer. I will just emphasize on this point a little. Friends, you are 2000 and among 2000, 13 to 1400 are from the state of Gujarat. And in our state, these students face a little difficulty with the language and we are in total support to them. Although we are going to take each lecture in English language, I am going a little slow so that my students of Gujarat can understand it very clearly. So you have to bear with it and I am sorry for that. And in this context, I even had a feedback, sir थोड़ा हिंदी भी कभी कभी बोला करिए. Sir, speak a little bit of Hindi also. Friend, we are working on the Hindi and the Gujarati version of this e-learning concept and we will come with a surprise in few days. So, with just justification and clarification, let us begin with a very important topic in chromatography and that is thin layer and paper chromatography. No need to introduce again. We will directly move to the concepts. Friends, whenever we are on the verge of discussing thin layer and paper chromatography, the very first thing that we should know is they fall under the category of planar chromatography. Now the first question prevails that how come they fall under the category of planar chromatography? Lecture of day 1 where we had classification, and in that classification if you have looked onto carefully the shape of the stationary phase where planar shape and column shape, and among that planar shape has included thin layer and paper with it. So thin layer and paper chromatography fall under the category of planar chromatography. The main objective of thin layer and paper chromatography lies within identification of the compounds, purification of the compounds, and segregation of the compounds. Friends and students, you would be aware of this word segregation, but let us make it little clear. Aggregate and segregate. Segregate means to separate, alag karna. Aggregate means to bring together, ek saath lana. So over here, thin layer chromatography and paper chromatography can identify from a mixture of compound, can even purify to an extent, not completely, but has the power to separate, segregate. So these are the main three objectives when we talk of thin layer and paper chromatography. Moving ahead, what is the position of thin layer and paper chromatography? Position is not a new word over here. It is just a part of classification to be discussed with you in a new way. Whenever I try to classify chromatography on the basis of the dimension of stationary phase. Dimension here has direct relation with the shape. We get two shapes, planar and column. And going into planar, we now have thin layer chromatography and paper chromatography. Generally, the thin layer chromatography or the paper chromatography we do, or rather we are going to discuss in this current scheduled video, is a one layer or a one dimension chromatography, but two dimension chromatography also exists. As I told you in the day one lecture, if you recall, that when we distribute or we fragmentized chromatography on the basis of the shape, it was planar and column, where planar is one dimension and two dimension and column is three dimension from my point of view. But over here, remember very well that whether it is thin layer chromatography or it is paper chromatography, it can be either written as one dimension or it can be explained as two dimension. Two dimension is a separate science, but as of now in this video we are going to concise ourselves to one dimension chromatography. So position of TLC and paper is inside the category of planar chromatography, which can be brought into existence based on the dimension or the shape of stationary phase. Thin layer chromatography. In thin layer chromatography, stationary phases. How can we define these stationary phases? Stationary phase over here in thin layer chromatography can be of two types. It can be a pure solid. You know now very well from the day one video that it works on the phenomena of adsorption if it is solid, or liquid coated on solid, which works on the phenomena of partition. So over here, mind very well, thin layer chromatography can be both pure solid or a liquid coated on a solid. But what are the different types of materials that can be used as a stationary phase? You can use silica gel with a binder called gypsum. I have already explained you. If not, I am explaining now. Silica gel G comes written or a sticker on the silica gel bottle where the last capital G stands for gypsum, and that helps in binding the silica with the surface as a binder, a type of a cement. Or you can even use starch nowadays, alumina, cellulose powder, acrylamides, and charcoal and activated carbon. These are few very important used solid stationary phase in the thin layer chromatography. Now comes the question that if you are using these types of solid stationary phase in the TLC separating technique, then what are the positive points they have? All these materials differ in their particle size. They are very minute in their particle size, up to a little values of microns, and hence it plays a very important role in the separation science. Their nature, ranging from non-polar to mid-polar to polar, also plays a very important role. If you look over here, you have cellulose powder. It can be polar. On the very contrary end, you can also use few non-polar samples like charcoal and activated carbon as stationary phases. Over here, homogeneity of this stationary phase is also very important. It has to be homogeneous. It should be mixed very well. Now, when to use this word homogeneous is coming after few slides, and at that time we will go in depth. But over here, remember very well, whatever be the stationary phase from the given, they are all supposed to be applied on a thin glass or aluminium plate. and hence they require some support like calcium sulfate to be applied on a glass plate or a alumina sheet. And this role of a binder between the support like glass or alumina and these stationary phases is played by gypsum. Right? What the concept, I think? Thin layer chromatography, stationary phase. Moving further with the mobile phase, whenever you have thin layer chromatography and you are trying to discuss the mobile phase, mind well you have two different categories of mobile phase and they are non-polar and polar respectively. Ethyl ether, petroleum ether, hexane, acetone consist or comprise together in the range of non-polar to mid-polar. Whereas chloroform, methanol, ammonia, water are few which comes under the category of polar. Friends, don't think in a way that sir you are putting acetone in non-polar, but it can show little polarity. This is not like a rigid science that this is polar, this is non-polar. It is a comparative science that one is more non-polar, second one is lesser non-polar. The lesser non-polar can be polar and the lesser polar can be non-polar. See what I am speaking. Listen to it very carefully. The one that is more non-polar is less polar and the one that is more polar is less non-polar. This is the beauty of solvents and these beautiful solvents are then applied as mobile phase in thin layer chromatography. Friends, thin layer chromatography experiment is a superb experiment. You need to prepare a TLC plate on which the experiment is conducted. Preparation of TLC plate using a stationary phase, silica gel with gypsum as a binder. In the first picture if you see, we are taking a small piece of glass and to that we are applying a slurry, a paste of silica gel and water. Now, when we use the word slurry, homogeneous comes into existence. When a solid powder is mixed in water or any damp solvent and it becomes a slurry which is very smooth, then it is said to have the property of homogeneous. So friends, a homogeneous slurry is applied on this glass plate and generally this glass plate is nothing but that small plate that microbiology people use while blood analysis on that microscope lens. Point number two, once you start pouring the slurry on the plate, you need to pour it on a clean glass surface and pour it uniformly. You can see the uniformation pattern is starting and then you can see a complete uniform pattern is formed. And then you have to allow it to dry in oven for at least 24 to 48 hours. Mind well friends, this one number, two number, three number and four number are not associated with these numbers. These are the steps to be performed by a student or a professor in the laboratory and these are the four snaps that were taken to show you how the slurry is coming onto the glass, how it is falling, how we are adjusting and how it is becoming a plain surface. But as said, animated videos or pure videos play a very important role in understanding how to prepare a stationary phased thin layer chromatography plate. So let's do it. Let's prepare.
Hello friends, welcome to the channel solution. In this video, we will show you the procedure for preparation of TLC plates. TLC plates means thin layer chromatography plate of which one side is coated with adsorbent. The most common adsorbents are silica alumina. Here we have taken silica gel G as adsorbent. For the preparation of TLC plates, first we have to prepare slurry of silica gel G by mixing 1 part of the silica gel G with 2.5 part of distilled water. It means if you have taken 1 gram of silica gel G, then mix it with 2.5 ml of distilled water to prepare slurry. Here we have taken 5 gram of silica gel G into the glass mortar pestle and then add about.
If you observe over here, in this beaker, the student has taken silical gel G powder, and now they are adding water or a suitable solvent and preparing a slurry. Remember very well, this slurry has to be homogeneous, smooth. Let's check it.
12.5 ml of distilled water and then mix it with the pistol to prepare slurry. Mix it properly to make sure that there are no lumps. Then after mixing,
There are no lumps, non-lumps. There should be no small pieces of that solid powder. It should be homogeneous.
transfer the slurry into the clean dry beaker and by using glass rod make the slurry homogeneous. With the help of pipette, pour small amount of the slurry on the clean dry glass plate and then move the plate around to spread the slurry uniformly over the glass plate and to form thin uniform layer of adsorbent of about 0.2 to 0.3 mm thick. Make sure that there should not be any uneven spot on the plate and remove the excess slurry over the plate. Similarly, you can follow the same procedure to coat the big size glass plate with the slurry. These TLC plates can be used for analytical study. It is used to identify the components of a mixture and also to check the purity of the sample. Move the glass plate so that the slurry get uniformly coated over the glass plate. You can see that the slurry is uniformly coated over the glass plate. After uniformly coating the slurry, then dry these plates at room temperature. After drying the plate at room temperature, then finally place the dried plate in hot air oven for about 1 hour at 100 to 105 degrees Celsius to activate them. After 1 hour, remove the plate from the oven. Now our TLC plates are ready for analytical study. It is very important to note that always use forceps to handle the TLC plates. Do not touch the silica layer of the TLC plates as it can damage the layer and also cause contamination. You can also store these plates protected from the moisture and you can use this plate within 3 days. Make sure that at the time of use, activate the TLC plate again. Thank you for watching this video. In the next video, we will show you the techniques of thin layer chromatography. Thank you.
So friends, this is a credit that has to be given to this institute who has prepared this video and posted on Google from where I have got it. When Madam was describing this whole process, she said that minimum 1 hour in oven, but you can use this plate after or up to 3 days. So from 1 day or 1 hour to 3 days, don't place it outside, keep it inside the oven. Henceforth I have written it sometimes needs to be placed inside the oven for 24 to 48 hours. She also spoke a word, don't touch it with hands, it will contaminate. Now this is very important being a science student. Our hands have a little bit amount of amino acids present on the layer. So when you touch it with your hands on the plate, they might get transferred and they might create an interference during the analysis or the visualization of plate. So always use forceps to handle them. Moving further, with a hope that you have understood it completely from this very interactive video, performing the TLC experiment. Now, once I have a TLC with me, how to perform the experiment? So, use stationary phase as a silica gel G with gypsum as a binder. Yes, we have done it. Mobile phase like methanol, acetone, acetonitrile, ether, ethyl acetate. Yes, you can take. Take a dry plate. Place the sample or analyte spot at the bottom with a capillary. Place it in a jar filled with mobile phase and allow it to run. Friends, science, nevertheless, is a very interesting subject, but animations and videos play a very important role. If I will directly read these 4 lines, they are of no importance. But for these 4 lines, here is a very interesting video, or rather to say animation. First of all, we were supposed to take a plate. On this plate, we were supposed to put with the capillary 3 different spots or components. This has to be placed in a glass beaker or a jar and it has to be filled with a mobile phase, mind well in such a way that the mobile phase should not touch initially to the spots. When into the beaker or a jar you are placing the plate, it should be placed in such a way initially that the mobile phase touches the bottom of the plate but should not get in direct contact with the mobile phase. And as and when you put it inside and take your hand out, you have to allow it to run. Whenever you allow it to run, you will see that the spots are moving at a different rate. Now, this is very important, that the spots are moving at a different rate. Why it happens so? And the answer is the phenomena of like attracts like, that we have already discussed earlier in the initial day one video. What has happened over here? Among these three sports, if we assume the surface for a while to be polar, then on the basis of the phenomena like attracts like, the polar white surface has more attraction towards red, and hence among the three components red has to be most polar. Then and then only polar can attract with a polar. Blue is moving at a faster rate, and if it moves at a faster rate, it has less attraction towards the stationary phase. And if your stationary phase is polar over here in the case of silica gel, then blue is the non-polar. And green did not move too fast nor too slow, so it is mid non-polar or mid polar. So this is how you can identify the samples. You can even segregate the samples in experimental technique of TLC. The example over here is an identification example. How? If in examination we are given a red test tube, a green and a blue because of the samples filled inside, and we are asked to identify which is most polar and which is least polar, we'll place the spot. We are knowing that the plate is polar, and hence we can judge that the spot that will move the least will be polar, and the one that is moving the faster will be non-polar. So this is the magic of thin layer chromatography. Friends, over here comes a very important point, and that important point is retardation factor. There were two things, retention time and retardation factor. Retention time was something that a sample requires to pass from one end of the column to another end of the column, which we already know. But when it comes to retardation factor, then it is the distance traveled by a sample from the lower end to its point where it stopped, whole divided by the distance traveled by the mobile phase from the bottom to the point where it stopped. So distance ideally traveled by a sample divided by distance traveled by a mobile phase always gives me retardation factor value. Remember one thing very well, that mobile phase travels the maximum. Mobile phase travels the maximum. Among the samples, none sample or no sample can travel more than mobile phase. This concept sometimes I explain to my students in a very lethargic way. I tell them that I will speak in Hindi. आप जब नाव लेके, when you carry a boat and move in the river, हमेशा पानी आगे चलता है और नाव पीछे चलती है. The water is flowing ahead and the boat is going behind. कभी ऐसा सुना है नाव आगे चलेगी और पानी पीछे पीछे आ रहा है? The boat has ran away and the water is coming behind. Not possible. Why? Because that water is a carrier for that boat. Similarly, mobile phase over here is a carrier for these samples. So always the distance traveled by these mobile phase will be more compared to the distance traveled by the samples. Yes, sometimes the sample travels equally to the mobile phase, but not more than mobile phase. How this concept will help each of us? It will help over here in retardation factor. See how. RF value is the distance traveled by sample or analyte divided by distance traveled by mobile phase. Now, RF value can never be greater than 1. Why? Because the distance traveled by analyte can be maximum equal to distance traveled by mobile phase. So if this is 20, this is 20, it is 1, but not more than 1. Otherwise, the distance traveled by analyte is always less than the mobile phase. So the numerator is smaller, the denominator is bigger. So the answer is always in a decimal lesser than 1. And sometimes it happens that the sample does not travel, it remains at the bottom. So it is 0 divided by 1. So friends, the maximum range over here for an RF value can be between 0 to 1. It cannot exceed 1 in any circumstances. And if does so, you have done a magic. Water is behind and the boat is away. It will never happen. So this should be kept in mind that the range of RF can never be greater than 1. See, over here I have mentioned values must be between 0 and 1. It should be greater than 0 and it should be lesser than 1. But friends, what is the ideal value? It is an average of several experiments. No one has written it that this has to be. But between 0.25 to 0.75, the value that comes is an ideal value. And these are the retardation factor value. Friends, RF value is 0. What does it mean? RF value 0 means the sample over here did not travel. In what case it would happen that the sample will not travel? In a case where your sample is tightly bound with the stationary phase. It means the nature of stationary phase and the nature of sample is very equal. Then the mobile phase as a carrier will not be able to make the sample move. So when the sample does not move, this value becomes 0 and henceforth RF becomes 0, and when RF becomes 0, we must say that the sample has a very high attraction with the stationary phase. So it is written over here. If RF value is 0, analyte has a high interaction with the stationary phase and no interaction with the mobile phase. If RF value is equal to 1, then the sample has no interaction with the stationary phase. It goes on running with the mobile phase. Why I am doing this way? Because it goes upwards. Yes, capillary action. Opposite to gravity, capillary action. Analyte has a high interaction with mobile phase and no interaction with distant phase. And highly soluble in mobile phase. Then and then it will move, otherwise it won't move. So this is what RF is. Remember very well, retention time was just the time taken by a sample to pass from one end of the column to another end of the column. But when it comes to the retardation factor value, it is the ratio of the distance traveled by the sample or analyte divided by distance traveled by the mobile phase. Friends, moving further, I am going to explain you a little bit of the affinity of these mixture on the stationary phase. If you see on the left, we are just going to start the experiment, and on the right, the experiment is done. We could see that when the blue color mobile phase traveled from the bottom to the top, the yellow particles moved the most and the blue particle moved the least. So the particles that moves the least have a stronger attraction or affinity to the white stationary phase. And the particle that moved the most, that is yellow, had the highest attraction with the blue color mobile phase and least attraction with the white color stationary phase. And this is explained very well by the box given below. Remember, the particle that moves the most in TLC has the least attraction with the stationary phase, and the particle that moves the least in the stationary phase has the most attraction with this the stationary phase. I'll repeat it once. The particle that moves the most in the stationary phase has the least attraction with the stationary phase, and the particle that moves the least with the stationary phase has the most attraction with the stationary phase. Over here, yellow particles are moving the most, So they have least attraction with the stationary phase, and the blue particles are moving the least, so they have the most attraction with the stationary phase. You can see over here, blue particle, no attraction with the stationary phase. It is written like this, but we have to check it once whether it is correct or whether there is a mistake. So this is a type of a trivia question for us. Look at the question. Over here, the blue particles are not moving. If the blue particles are not moving, what is its affinity with the stationary phase? It cannot be dash dash dash, it has to be maximum. So over here, that has to be a large number of tick marks. Large number of tick marks has to be replaced over here, where we can say that it has the highest affinity with the stationary phase. So this blue corresponds to these blue having the highest affinity with the stationary phase. So here there has to be the maximum tick marks. Remember very well. Over there, yellow. It has the least affinity with the stationary phase but has the highest affinity with the mobile phase. Whereas blue, which has to be maximum ticked because of the highest affinity with the stationary phase, has no affinity with the mobile phase. And remember, when the sample is insoluble in mobile phase, it will not move. When the sample is insoluble in mobile phase, it will not move. So this is the aspect of attraction in TLC, that is thin layer chromatography. As I told you earlier, always remember that whether it is thin layer chromatography or paper chromatography, mobile phase always acts as a carrier and whole separation mechanism is based on the nature of stationary phase. Over here, we are calculating the RF value. The line over here suggests the distance traveled by mobile phase, and over here the spots suggest the distance traveled by the samples. Friends, do not compare the line with the scale value directly or you will get confused. Okay, sir, somewhere it is between 8 to 9 and here you have written 7.7, but the scale is starting from 1 and not from 0. Understood? You got what I'm speaking? Here it is 7.7, that is distance traveled by mobile phase. Here it is directly 8.7. So you might get confused. Sir has made a mistake of 1. But no, I have not made a mistake of 1. Mobile phase distance and sample distance are not to be calculated from the bottom of the plate. They are to be calculated from the place where the spots were placed. And spots are placed little up so the mobile phase does not touch. So the spots are placed here where the value is 1. So 8.7 minus 1, it is 7.7. And here the distance traveled is 1.4. Here it is 6. And here it is 6. And here it is 4.1. Now the question comes. When the spot is too large, will you calculate from here or will you calculate from here? You will always try to calculate in such a way that you focus at the center. I cannot calculate from the bottom, I cannot calculate from the top. I have to calculate from the center, and the center is somewhat around 5.1 minus 1. I will end up with 4.1. So friends, this is how you calculate the RF values, and RF value will help you in determining the nature of the sample. If RF value is more, the sample has less attraction with the stationary phase. Remember very well what I am speaking. If RF value is more, the sample has less attraction with stationary phase. Let us check over here. Spot 2 has the highest RF value and hence it is running faster, and if it is running faster it has the least attraction with the stationary phase. Hope you are getting what I am speaking. What are the factors that affect the RF value? Temperature, solvent, concentration of sample, thickness of the layer, and impurity in the sample. See over here, this plate, after making the spots, you have to keep it in such a place to run where the temperature is moderate. If temperature is too high, then the spot might get evaporated a little. Point number 2, solvent. Solvent should be such which gets least evaporated, or you have to close with a watch glass. Concentration of the sample. The sample has to be placed in a very less diluted concentration. If you get a sample, you cannot directly take the sample with the capillary and make a spot on the TLC plate. First, you have to dissolve that sample in the mobile phase that is to be used in the experiment. Your sample has to be soluble in the experiment. Your sample has to be soluble in the mobile phase, and then only that sample which is diluted now with the mobile phase can be used as a spot, and it should be a very small spot with a diluted concentration. Then thickness of the layer. This TLC plate should be a thin layered plate, and after that you should have least impurity in the sample. If your sample has impurity, then you might get two spots, one of the pure sample and one of the impurity present. So these are the important factors that might affect the value of the RF, might affect the distance that a sample travels. So friends, how can we know that what is the distance traveled by the samples? If the sample are colored, sometimes you can see with your naked eyes. But if the samples are not colored, you have different methods of visualizing the samples. Over here, while visualizing the samples, there are different methods of visualization. Method number one is the destructive method of visualization, and method number two is the non-destructive method of visualization. Non-destructive method of visualization means a TLC plate, once visualized, can be visualized after and after, and the spot remains as such for a while. And such a method is a UV light source of shorter and longer wavelength that can be used to visualize your plate. And this is generally called a UV cabinet or a UV chamber. But there are some destructive methods. What are these methods? Sometimes when the spots are invisible, to make them visible, you spray it with few compounds. They are sulfuric acid, ninhydrin, iodine. While spraying with ninhydrin, iodine and sulfuric acid, the sample gets oxidized. It means you have destroyed the originality and the nature of sample, and you are taking the new version of sample. So when you destroy the originality of the sample, it falls under the category of destructive methods of visualization. But a UV source is not considered as a destructive method of visualization. So this is how we started from the preparation of the plate, making the spots, allowing it to run, measuring the distance and visualizing it with destructive methods of visualization and non-destructive methods of visualization. Friends, up till what I know, ninhydrin is used when you want to visualize amino acid spots. Iodine is used in several organic reactions for visualization. Friends, when I was going through the feedback that came from your side on the day one, there were few feedbacks where it was said that, sir, if possible, shorten the video. I am not going to shorten the video, but for your sake, I will divide the video into two parts where it can be. Over here, the title of the topic was TLC and paper chromatography. So, I'll make this video into two halves. The first will be TLC and the second will be paper. So, friends, over here, probably we have come to the end of TLC, that is thin layer chromatography. We started with the stationary phase in thin layer chromatography, then we came to the mobile phase, then we started with an experiment. We also saw the video of the experiment, performing the TLC experiment. I will repeat this so you can just get an idea what we were doing. So here comes the distance of mobile phase from here to here, and stationary phase, the samples from here to the distance they travel, which can be calculated as RF values, not from the bottom of the plate. We calculated and we learnt about the RF values, the concept of affinity, a mathematical experiment, or rather to say a mathematical calculation, factors affecting RF value and visualization of TLC. So friends, this much is the topic that has to be covered in TLC. When we will move further, we will start with paper chromatography. And before that, we will end with this slide, and that is application of TLC. It is used for the purity of the sample or analyte testing. You can check the purity of the sample. Just now we said that if impurity is present, you will get two spots, one of the pure sample and one spot for the impurity. Identification of the compound qualitatively, whether your compound is polar, mid-polar, non-polar. Evaluation of the reaction process. This is the most important thing organic students do. They start with aniline. They are preparing acetanilide. They will take a spot of aniline, they will put a spot of acetate lead and allow it to run. And then they will compare the product spots with the reactant spots. Product spot is always different from reactant spot, but sometimes on the way of product spot, you find a light dot of reactant. And hence you say that still allow the reaction to move further. So this comes under the category of evaluation of reaction process and checking the performance of other separation process. So friends, this was all about thin layer chromatography, and this will now be known as the part 1 of the video thin layer and paper chromatography. In the very next video, I'll directly start with the paper chromatography, and hence when we will end thin layer chromatography and paper chromatography, we would have done with the two important topics that fall under the category of planar chromatography. Thank you.